Session 3 and 4 taught by Dr. Reams in Black in 1977. This is tape 26 side B.
Brings us to the subject that we were talking about this morning. Is it mind over matter, or is it matter over mind? Which has the most bearing? Does the mind have more bearing on the matter, or does matter have more bearing on the mind? Which comes first, matter or the mind? Matter. Now, in the prisons, there are men that are incorrigible. I mean, they are dangerous to even let them out. They even have to hand their food on trays with a long handle to them, because they're not insane. Their body chemistry is upset until they're in such conflict with themselves, until they would be dangerous to let them out of there. Now, I believe that through a diet, a lot of these men could be rehabilitated. They could be tamed. You can take diet and feed guinea pigs so that they'll chew each other's ears off and even bite you if you put your hand in the pen, and then you can feed them another diet, and they'll be as tame that any child could pick them up, whether the guinea pig knew the child or not. Now, this is the effect of diet upon people. And I've already in this class briefly told you what brought about a revolt against society, against yourself, what caused people to become alcoholics or hooked on dope, or to be out of control of their better judgment. And it's in the tape. Read it and find out what we said about it. But one of the great things that's been very difficult in this class, we have covered so much material in 2 classes so quickly, until if you're not confused, I don't understand why. I don't understand why. You've covered too much material in too short a length of time. For instance, I'll give you an example. When the airplanes first come out, they only had a compass on them, and then they had an altimeter, and then another instrument. Then finally they got a gas gauge on one to show how much gasoline we had. We didn't even know at first how much gasoline we were using until we got back down. Of course, we didn't fly very far, just up for amusement. That's all the flying was for. And those small little planes, a big plane, had not been made yet. And when they made a plane that would carry 10 passengers, even the preachers complained, because, suppose it would wreck, it would kill 10 people all at one time. This really happened. It really happened. So, I mean, all of the complaints that people make, and yet you're wasting your time if you make a complaint that you can't do something about. It's time wasted. So if you have something that you think is worth complaining about, it's nice to ask questions to see if you can get the answer, but if you can't, then start working on it yourself. It's a problem that God's given you to solve. Now, also, indigestion is the beginning of most illnesses. Now, I don't mean acute indigestion. I meant the lack of digestion, the lack of getting the minerals out of your food. Now, we have told you that there was 2 main purposes for this. One is the lack of calcium, the other is lack of oxygen. This is the beginning of problems, and many times they begin in childhood. And they cause children to form habits that become stumbling blocks throughout their entire life. And many times they have genetic effects, or not genetic effects, but effects on I shouldn't say genetic, they have, well, indirectly do, but it won't show up until the next generations. It has effect on the various glands in our body, approximately 284, and the best thing I know to call these glands is transformer glands. There's only a few of them been named. But to call them transformer glands, now these glands, then, whenever it's time in life for these glands to become active, then they don't. They don't act, or they overact, or they come into production too small, too quickly. For instance, some girls come into puberty at 9 years old, even 6 years old. There's medical cases where one that I know of that came into full puberty at 6 years old. There's one case of a man that came into full manhood at 4 years old and died of old age at 6 with a long beard and a bass voice. And so, in other words, these glands in our body determine at a certain age it will do certain things. For instance, boys and girls that are born normal use the same amount of calciums until the young lady comes into young womanhood, and at that time she uses 700 times more per day than a normal man. And if she keeps this ratio throughout her life, she will have a very happy life as far as health is concerned. But if this calcium drops too low at any time she's in menopause, it doesn't matter whether it's 10 years old or 60 years old. So it's menopause. When the calciums drop too low, she becomes too nervous. So therefore they magnify women's diseases over men. Most doctors do, because they don't know to supply the calciums that they're needed to keep them healthy. However, when a man's calciums gets too low, he's dog tired at night from barking all day. So he's upset also. So these calciums that we have and are needed to maintain our perfect health and life goes back to the responsibility of the farmer. And he hasn't been taught to put lime on the ground, because there's no money in lime. It's only about $6 to $8 or $9 a ton delivered. And many times they'll apply it on your farm for that much. And yet, the experiment station says that if you have a pH of 7, you don't need lime. When white sand itself has a pH of 7, water, pure water, distilled water, has a pH of 7, it doesn't have any calcium in it. pH is a measure of resistance, and it is the resistance in our body that gives us energy, that brings this about. And energy is like the parts of a jigsaw puzzle. I'm in review now. And as the various forms of energy are put together to form the micronage or a molecule, they are in such great proportions until you can't express them in numbers. You could express them in algebraic terms, but algebraic terms are so wide and so big until it would be very difficult to know exactly where you are. Or exactly, no one knows exactly where they are, but they know the close range of where they are. It's through logarithms that we calculated the range of the ranges. In other words, it is through the logarithms that we were able to calculate the 5 ranges. It's through logarithms that we were able, with comparing it to the frequency, that we knew that theory was right. In other words, we can prove that theory is correct. It is through logarithms that we determined that our body temperature should be between 98 and 99 degrees Fahrenheit to be normal temperature. It's through logarithms that we determined that an anionic body had a temperature of 980 degrees centigrade. So there's so many things that you can do with logarithms. And in fact, they're easy. Very easy to handle. We're only handling the simple ones. There's many different kinds and uses of logarithms. It's also the basis for a slide rule. Logarithms are the very basis of a slide rule. So you can learn to use a slide rule without ever hearing of a logarithm. But they're the foundation basis of use of a slide rule. So the more you know about them, the more benefit you'll see. Suppose that you should pick a native up out of the middle of Africa that had never seen an automobile, and there's some over there that still yet haven't seen an automobile, and show them a bag or a box of mechanical tools. Would they know what they are? They'd have no idea what they were until they saw an automobile, and then saw somebody using it. And then they begin to comprehend what the tools are for. But let's take a very highly educated professor in the United States, maybe he's a dietitian, and put him in the midst of Africa. I imagine he'd have a pretty hard time making a living over there, trying to figure out the way the native lives, and he would be subject to all kinds of diseases because he wouldn't be immune to the diseases. he would have all kinds of problems. Now, education is in your own environment, determining how to master every situation. Because to say that the native in the forest is ignorant is an understatement. He's ignorant if you want to compare him with a college professor or someone that can read or speak many languages. Yes, what are you comparing education with? Education is simply a bag of tools to work with. Logarithms are part of the tools you're going to need in the future courses. So if you don't know what the tools are for, never seen them in use, I've done my best to tell you what they're about and how to use them. And now let's look back to our matter, mind over matter, or matter over mind. Matter over mind comes first. Now, there's a certain amount of things that we say is natural or instinctive. In other words, our heart beats naturally. We breathe naturally. We walk naturally. We go to sleep and we sleep naturally. We do many things very natural. A hen lays an egg, very natural. She doesn't know why she lays an egg, but she lays an egg. And the poor little old hen's only got a thimble full of brains. So she gets up and she tells the world, cackles for 10 or 15 minutes because she's so happy that she laid an egg. Old Brother Fox is out there in the woods. He knows that hen laid an egg, so he comes and hunts the nest. And he eats the egg. If you didn't, there'd be so many chickens on earth, there wouldn't be no room for foxes. So the balance of nature. The balance of nature. You see what I'm trying to get at here? Is that through the study of the energy that makes matter, we can comprehend the balance of nature. The balance of nature. To say that there's a perfect balance is an understatement. There isn't any such thing as a perfect balance. Why? Because no two people have the same requirements. There isn't any such thing as a perfect balance of food, or drink, or water, or exercise, or fruits, or anything else. There isn't any such thing as a perfect balance, because our requirements are all different. Now, if you don't know what those requirements are, and you don't know how to express them mathematically, how can you correct them? Mathematics is the most perfect science that there is, and it's got a lot of mistakes. That is, or at least a lot of people make mistakes with it. In fact, let me say it this way. You cannot break the laws of physics. You cannot break the laws of God. That is impossible, but you can break yourself on those laws. Is that clear? You can only break yourself on those laws. Now, the more you understand the theory of these laws, the easier it is to obey the law. But if you don't understand the theory of the law, how can you obey it? If you don't know where you're going, how do you know when you get there? Do you see what I'm saying? Now, there's one purpose of geometrical math. There's 16 things that you can actually prove in geometrical math. And the Pythagoras theory is the 16th one, in which involves all the other 15 principles bound up into one principle. Now, geometrical math, plain geometrical math, lets you know when you get the answer. Otherwise, you wouldn't know. You just keep on going. Did you ever start to go to a city, especially on these big highways, and pass it and didn't even know you passed it? Well, you didn't know when you got there, because they lacked some signs, cosines and geometrical problems they left out. Somebody left or taking a sign down. A few years back, the teenagers got a great idea of moving signs from one way to another to confuse tourists. Then they formed a signboard club in which a stop sign brings $25. And they think they've got a sign collectors club now in the United States in which they collect signboards. And they think it's great to collect these signboards, but actually their parents don't tell them that that's wrong, that that's stealing. But it's a club and it's in existence. So learning what is yours starts with youth. Now learning what you need is education and supplying it. So supply and demand is what this course is about. Supply and demand. In other words, know what the demand is, so the supply and demand then becomes the base for cause and effect. Isn't it easy? Isn't it logical? Doesn't it make sense? Doesn't it make sense? Are you ready to tell them about logarithms? Okay, let's do that now.
To all of you. Yeah, very much. I need to know how many of you in this class can work the evaluation of this expression by converting it to a logarithmic equation and then evaluating it. Now, those that have had engineering, physics, or any kind of engineering at all, how many can do that, please? Because I'm looking for helpers. Okay, 1, 2. Okay, you got 1, 2, Bob, 3. All right. Okay, fine. If during this thing at the proper time, if you fellows would just circulate, and then those that need help, because obviously, as Doc has told us before, there's no way he can get to teach each person individually. I can't get to you individually. So if you have a hang-up on something and we get further along in the calculations, I didn't put this up here to scare you. I'm going to show you how this is quite within your power to do this morning. Don't copy it down or anything. You'll scare yourself to death. We're a long way from that. Okay? But I needed some help so that people can answer questions. Let me tell you just a little bit about my philosophy of education and teaching. In a classroom, there has to be all kinds of perception when something is said and receiving information from someone that's speaking. And we know that in an audience of any size, at any time, you've only got 30% of the people listening to what you're saying. That is a true fact. Give or take 10%, so what's the difference? We're still under half. So what I'm asking for this morning is 100%, because what we're going to do is attempt to go through about 10 class hours of time in an advanced algebra class in whatever time Doc will allow me to go, and each one of those hours will represent 2 hours at home, homework on those problems, so we're going to cover 30 hours in whatever time we have here. We have the month of July. Okay, we're going to concentrate this thing as much as possible. Now, it's my idea in education that if you have a question in your mind, at any time, the time that question must be answered, if it's on the subject that we're dealing with, must be asked at that moment. You will not irritate me by asking questions. There is no way that, yeah, if you don't ask any questions, there's no way that you can run me out of patience on this, except by holding the question until 3 sentences or 4 steps later. Okay? Because you know what's going to happen if we do that. Then we have to revert back to where we were before, and you know what it's like to stop John Black when he's right in the middle of a long thing, and then he loses it, and you got to go back. And this, you will see the same thing. We're going to have to go back to that point and pick up again. So when we get momentum, we'll have to keep moving. So if you have a question, please write then, and I won't be able to see your hand because this thing sort of blinds you. So just yell out, hey, or whatever, question or whatever. We'll stop right then, get it, and then immediately proceed. Is that agreed? Okay. Are there any questions? So far, okay. All right, just a quick review of what we did the other day on base 2 logarithms. Some people thought that what we were getting into was modern math, and we talked about base 2, computer language where we use only zeros and ones, electric switches on and off. That's not it at all. Okay, base 2 would be the type of people you would have if somewhere out on the South Pacific island all they had was an index finger in this hand, an index finger in this hand, and that would be the extent of their counting. Okay, we have base 10, probably, because we have that many fingers. In some South Sea islands, maybe Doc could even tell us where it's heard about there, everybody on the island has 6 on each hand. And guess what base they work in? Okay, now the Babylonians worked in the base 60. Conclusion? Okay, so you see sometimes logic breaks down if you don't have enough information. Okay, here we go. We had our table built with base 2. 2 to the first power was 2. 2 to the second power, 4. 2 to the third power was 8. Now please take a moment to make about 10 entries on that. Discovering you can fill that in very quickly because it's just 2, 4, 8, 16, 32, 64 as you had the other day. On to about 2 to the 10th power, did you get 1,024? Okay, add just a couple of more, go on up to the 12th power. Everybody got that? All right, now, let's go back. I left a blank space up here. I don't know whether you did or not. Let's put in the 0 power here. And what would 2 to the 0 power equal then? 1. All right. Okay, the logic holds here. Count backwards and cut in half as you're going. Okay, 8, 4, 2. If you cut that in half, you would have 1. Now, I can explain why. I'm not trying to avoid the question, but it's not counterproductive. Just fill in the table. Any number, any base raised to the 0 power in geometric math is 1. Okay? Now, you could expand this table by going backwards, and Doc did refer to some problems the other day on energy loss, where he used a negative exponent in the base. So let us go upwards in this table, which is not there, and put some in. The negative 1 power then, which would look like this, written in the exponential form, 2 to the minus 1 power. Now, one of the first steps is to be able to write that thing with a positive exponent. And you noticed what Dr. Reams did the other day when he had 4 to the negative 4 power. A fraction appeared up there with a number in the denominator. So this would be written as 2 to the minus 1 power is written as 1 over 2 to the first power. Therefore, 2 to the negative 1 power equals what? 1/2. Okay? 2 to the negative 2 power. Now let's just take this, look at it like this. 2 to the negative 1 and write it over 1 as the denominator. This is just a little mechanical trick now. Invert that expression so that you have the 1 on the top and the 2 in the bottom, except that when you invert the thing, the sign on the exponent changes to the opposite sign. So it would become 1 over 2 to the second power. 1 over 2 squared, so the evaluation here is that 2 to the negative 2 power is 1/4. Does that make sense to everybody? Okay, do you have a question that we can help you with a little bit? It's just a pure mechanical trick. I'll show you can do it. All right, write this down, man, and everybody. 2 to the negative 5 power over 1. Now, how do you write that with a positive exponent on it? Rule. Invert. Okay? And at the moment that you invert, change to the opposite sign. Oh, okay, opposite sign. Define the term. There are only plus and minus signs in this. So change it to the other sign when you invert it. It's done simultaneously. So that becomes 1 over 2 raised to the positive 5 power. The evaluation then is that 2 to the negative 5 is equal to 1/32. Okay. 1 over 2 to the 5th. And what do we mean by 2 to the 5th? I thought this was clear. This tells us how many factors, and what are factors from yesterday, or the day before? Multipliers. So what you have is 2 times 2 times 2 times 2 times 2. There's 5 factors of 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay, is that clear then with everybody? That got you through. Okay. Now, we don't need to go further in the table than that to do some little problems to lead us into base 10. Or in relative math, it will become base 1 because we'll drop the 0, and Doc will have to make the transition to that. I have not had enough time with him to get the relationship of everything. Because when you are trying to follow someone from mountain peak to mountain peak and running like crazy in the valley, you know, it's difficult to keep up. So I'm going to try to take you through the valleys with me, and we'll run up and try to get to the peak. All right? All right, here we go. We can do problems with logs like multiplication, division, raising to a power, or taking a root. Everybody knows what multiplication and division is. There may be a few people that have not had raising to a power. We've just been raising numbers to a power. We raised 2 to the 5th power a moment ago, so that's what we mean, raising it to a power. It gets slightly more complicated when we raise to fraction powers. We'll get into that later. Taking a root, then, is finding that number which is the number that if raised to the index that you're talking about would give you the number you started with. Is that clear? No. So what we do, the sentence is not important, but what is important is to write one down, show you. All right, here it is. 9 raised to the 3/2 power. Now, you don't have a 3/2 in the log table, and you are wondering how, if I defined this exponent as the number of factors you have as 9, then how do I write down 9 3/2 times? We do it differently. We break this apart, and this number in the bottom, the denominator, becomes the root index. In other words, what you're looking for here is the square root of 9. The bottom number, the denominator, is asking for which root of this base that we're considering. And the square root of 9 is what? 3. Why? Because 3 times 3 is 9. That's why. Then what do you do with the 3? We've got it to the square root. You raise it up to the power that's in the numerator. And 3 to the 3rd power is 27. Is that clear? Repeat it. The denominator is the root index. In other words, you know what a square root is now. It's that number which, if multiplied by itself, which is poor mathematics language, what we're supposed to say is, it's the number which, if taken as a factor twice, if you get the liaison, would produce the number that you're looking at. So the square root of 9 is 3, because 3 times 3 is 9. The square root of 16 is 4, because 4 times 4 is 16. The square root of 49 is? Why? That's right. The square root of negative 36 is what? 6? Okay, this is a foul ball mathematically, isn't it? We have now moved into a new realm of imaginary numbers. You cannot find a number in the real number realm which multiplied by itself or used the factor twice will give you negative 36. I have a feeling we may get into that later. I don't know if there's anything in the imaginary realm. Yes, sir?
Could you give that right now?
Yes, if I can remember it. Some time has elapsed. The symbolism? And see, it's gone. Okay, just what is referring to? If you can get me started, what was I saying? Okay. Well, let's see. Tell me when I get to it. We had 9 to the 3/2. Was that the subject at the time I was talking?
You wrote down root. You wrote down raising in the root.
Yeah.
And you gave a long sentence on root.
Okay. I think that what I said was it is that number which, it's on the tape, it is that the root of a number is that number which, if raised to that power that you've used as a root, would give you the number. Simple example, 16 to the 1/2 power. This is the same thing as asking for the square root of 16, which is 4. So what I'm saying is that the root of the number, which we now know is 4, is that number which, if raised to this power of 2, produces the number that we talked about. And that's a very confusing way of saying the square root of 16 is 4. Then I expanded into this idea where the logarithm or the exponent is a fraction, and that you have to relate the idea that the denominator in this exponent or logarithm is the root index. The number up here then is the power that it would be raised to. In other words, a root index is the antithesis, the opposite thing of a power. Let's see if you've mastered that. What is 1,111 raised to the 3/3 power? Excellent. Okay. Of course. It's the same number because I took the cube root of 1,111 and then erased it to the third power, and we're right back where we started. In other words, in the third grade, if you ask somebody to say more simply, what is 3/3, they would say, you hope, 1. So, any number raised to the first power is what? It's itself. Okay? Any questions? All right. Now let's do a couple of calculations. I was going to spend like 3 minutes on that base 2 thing, and you see what it grows into. It just, see, what happens, this is what Doc is trying to say when people say, why don't you write a book? Because he starts down a line like this, and as soon as you get to this point, there is a case which you have to talk about, so you go like that. Now that left this undone. But this undone also had these things to it, which also had these things to it, and then he told us he'd have to write a book on everybody. Do you understand why he says that? Because you've seen a demonstration here that I got away from base 2 in order to explain a logarithm, an exponent, and we aren't even back to the basis yet. So you'll have to fill in some of these gaps, and I'm trying to make the gaps as small as possible. All right, let's do one problem each, a multiplying, dividing, which I think that you've got, and then we'll do some taking of roots and then raising to powers. When you get into the more complicated problems, you can remember this sentence as to what to do first, because the expression that I put up here at the first, which was the 7th root of some complicated looking number, you're wondering, what do you do first? Okay, I can give you a little sentence that tells you what to do first. That should give you comfort. Please remember my dear Aunt Sally. That's the sentence. Please remember my dear Aunt Sally. Underline the first letter in each word. Now, in logarithms, you can forget Aunt Sally. And no, don't write that down. Okay, communication problem. What I mean is, in that sentence, you may scratch through the 2 words Aunt Sally because we won't use them in logarithms. But we do want, please remember my dear. What do you think dear stands for? M, R, and P, the roots and the powers. And this is the order in which you will do them. When you have something to be done, you'll raise a number to okay, please remember my dear. When we have those things involved in a problem, we will want to do, in any tight little expression, things which are related together, we'll want to start down here and do the multiplications and the divisions that are expressed first. And we'll do them in the order in which they come. Otherwise, we'll get a different answer. So if you have a combination of a multiplication and a division, you do them just in the order they come. If the multiplication is there first, you do that. If the division is there first, you'll do that. After that is done, if there is a root to take of that expression, that would be the next thing to be done. And if you're going to have all of those things involved in giving you a number, which is to have its power taken, you would take the power of it last. We'll explain it better when we do a problem like that. All right, first problem is multiplication. Look at your base 2 table and multiply. Don't do it by writing it down. We want to get some practice here now so we can get ready for Doc's things in class 7 and 8, okay? Do it mentally, but look at your table. I want you to multiply 32 times. Now, when I write numbers like this in parentheses, I'll leave the X out. Times 16. All right, you should have the answer already if you're looking at your table. Okay, in your table, you found, next to the 32, you found a 5 there in the logs, right? And there you found a 4 written alongside. You got a 5 and a 4. What do you do with them? You add them. Add the multiplication, you add them. That gave you 9. Okay? And 2 raised to the 9th power is 512. You see, now truly, do you see how easy that is? You lost that. Okay. Okay. All right. Okay, I'll slow down. What I asked you for was 32 multiplied by 16. 32 in your table has a 5 written alongside of it in the column entry, doesn't it? What is that 5? It's the log. It's the power, but we have switched from power or exponent to calling it a log. It's the same thing, but we're going to call it a log. It's a logarithm. Now, what is the number that corresponds to the 16? It's 4. Here we multiply the numbers, but over here with the logs we simply add them. Okay, that gives you a 9. Now look in your table. In the log column, find the 9. Just look down. You got it? Okay, find the 9. Now look over there and find the anti-log. 512. You've got it. Okay? Okay, one more problem now. We can take more than 2 numbers multiplied together. Ready? Okay, multiply 4 times 16 times 16. Okay, and the answer is 1024. Okay, we'll analyze it. There's some people. Okay, how many know exactly what we did to get, or no, we'll put it the other way. How many do not know how we got that answer so fast? Okay, all right. Be honest. You've got to be honest or we can't make progress. What is the log of 4, please, out of your table? 2. What's the log of 16? 4. The log of 16 is 4. What do you do with numbers when you're multiplying? Add them. 4 and 2 gives you 10. 2 raised to the 10th power equals. Look in your table for 10 and find the anti-log. There it is, 1024. Okay, we're getting closer and closer to the 7th root of that thing I wrote down first. Ready? And please stop me instantly if there's a question, because we're going to start moving now. I'm going to simply say to you, because we need some knowledge transfer now, make this gap. Leap from a little stone to the next stone. What is 16 divided by 2, doing it by logs, and do it by logs, and which simple mathematics operation do you have to do now? Subtract. Okay, subtract. I think I said 16 divided by 2. The problem for you became what? 4 minus 1 gives you anti-log 8. All right. Okay. What is the log of 16? 4. What is the log of 2? 1. When we're dividing, we subtract the logs. Find the difference. How many steps between 4 and 1? 3. What is that 3? No, it's not 8. What is the 3? It's the log of the number, which is the result of this division. See, it's small enough that we know that 16 divided by 2 is 8, right? The number over here, the result of the subtraction, is the logarithm of the answer to the division problem. This is why Doc can calculate so quickly the energy levels, and I wish I could do it. Don't you? All right? But we have to start somewhere. Yes, sir. Doctor? Okay. Now can I combine multiplication and division problems into one problem? We'll see. And as soon as you... Not that table. He uses relative math and goes back to base 1, throws out all zeros, and that's what we're trying to raise ourselves up to. Because, see, in the geometric math... Okay, let me just take... No, I won't do that. I'll keep going. All right. Let's do this problem. 16 times 32 divided by 4. Now, as you look at this problem, the multiplication came first as I did it. You got 16 times 32 divided by 4, so the problem simply becomes what, please? I want one person to please raise your hand and tell me what to write down. Okay, the pilot from Alaska. You said almost everything right. Okay, 4 plus 5, which is 9, minus 2, gives 7. And he said that would be your answer, which is 128. Okay, we want more precision. The 7 is what? Okay, the 7 is the log of the answer to this problem. And you look in your table for the 7 and get the what? The anti-log. And that is the answer to the problem. All right. We'll do one more combination problem that way, and you write down the correct answer. Don't write anything else but the correct answer to the problem. Now, I want the answer. You just get to the log.